So this is the part 2 of the 2019 triple hire. And then we've got a Hertzsprung-Russell diagram here with a lot of information on. I'm sorry that the print is not the best here. Hopefully it'll be better on yours. But just a recap on the Hertzsprung-Russell is that the luminosity is on the y-axis and it's a logarithmic scale. So you can see it goes up in powers of, to the power of 2, 3, 4, 5, and then jumps up to 8. So we've got to realize that, and then you've got temperature is hotter this end than this end, so decrease in temperature up here. The main sequence trend is here, so R star should be around about by here somewhere. Not that I can see it, I don't think I need it. And then you've got the supergiants, and then you've got the white dwarfs region here. So that's just a quick recap on the diagram. So for 3 marks, we need 3 correct ticks. The larger the mass, the longer its lifetime. Generally, and I think this is something we need to know, that the bigger the mass, the faster it burns. So generally, it's got shorter half-lives. There are exceptions to the rule, but there's no evidence of that from the graph anyway, because it says use the HR diagram, so there's nothing about the speed at which they decay or burn. The largest supergiant is Betelgeuse, that's correct. So you can see that Betelgeuse, it's got the solar radius there, 10 to the 3, and it falls on that line. So it gets bigger as we go up that way. The radius of a white dwarf is approximately 100 times smaller than the radius of the sun. Well, the radius of a white dwarf is going to be 10 to the minus 2 there. And where it looks like we're going to need our sun. There's our sun, look. And our sun falls on the line that says lifetime. So 1 solar radius. So yeah, so to the minus 2, that's 2 zeros, isn't it? So that's 100 times smaller, 10 to the minus 2. So the hottest, oops, didn't want to do that. Let me just get the correct tools. The hottest star is Beta Centauri. Let's have a quick look. So we're looking for temperatures down here this way. So the hottest, so Beta Centauri I'm looking for, I think it's there. Yeah, and that looks it's the first one there. So that's got to be correct. And then, so these two has got to be incorrect, but we can just check it anyway. Centauri is too big to become a supergiant. Is big enough to become a supergiant. Let's have a look. Centauri A. I need to find it. Anyway, it's going to be wrong. I mean, we can prove that. It just takes a bit of long. And the redder the star, the hotter it is. And we know that the redder the star, the cooler it is. Okay, so for 3 marks, it's claimed that our sun leaves the main sequence. Its surface temperature will increase in the next stage of its life, decrease. Explain whether you agree with this. Well, we don't agree because, we can get all this from the graph. So I'm using the Hertzsprung-Russell diagram to do this. So currently the temperature of the sun is between 5,500 and 6,000 kelvins. Okay, so all this I'm just getting from this graph here. When it becomes a red giant, the temperature is going to actually decrease between that. And when it becomes a white dwarf, it's going to increase between that and that. And again, all this can be found on that Hertzsprung-Russell diagram. Explain in terms of named forces the changes our sun will undergo as it leaves the main sequence star. So first it's going to become a red giant, where the gas pressure is going to be more than the gravity, or the gravitational pull. So it will expand, and then it's going to become a white dwarf, where gas pressure is less than gravity, so it's going to contract and become smaller. Explain how the life cycle of stars contribute to the origin of our solar system. So during the supernova stage, in the life cycle of a star, the material, including all the heavy elements, so everything gets made in that supernova, heavier than iron, they're going to be returned into space. It's one massive explosion, and then the solar system is going to collapse under the force of gravity. All these clouds of gas and dust are going to collapse under gravity, and they're going to start forming a new solar system, or new planets, or new stars, and that is pretty much how it all works. I'm going to just press pause a minute because of the noise outside. Okay, Question 6 then, nuclear decay, fission. Fission reactors leads to production of vast amounts of electrical power. Okay, explain how the reactor is designed for it to be sustained and controlled for 4 marks. So we need to mention that a graphite moderator is going to slow down those neutrons so that it can be easily absorbed by the fuel, which probably going to be uranium. I don't know if it said that. So you could just say fuel atoms instead of uranium. And then the boron control rods are going to absorb the excess neutrons, the release from fission. Remember, fission now probably going to release 3 neutrons for every time a neutron runs into the nucleus of an atom. It's either going to be 2 or 3. So what are we going to do with those extra neutrons? We need to get them absorbed, and that's how they are absorbed with the use of a control rod. So it's going to keep that reaction constant rate. Not that I've needed to do this yet, but you can see that, oh yeah, I do, because I need to balance the equation. So I've got 1 plus 235 is 236 this side. That's going to equal 140 plus 94. That gives me 234. So I need another 2 neutrons to make up that 236. Again, I'm going to press pause a minute. So we can see on the bottom, 92 there, 54 plus 38, 92 there, so it's going to be 0. So it's got to be a neutron. We know that neutrons released. So we've completed the equation. Explain why the nucleus undergoes fission when it absorbs a neutron. So it's all to do with this imbalance, and that's why a radioactive element becomes radioactive anyway, because of that imbalance between a number of protons and neutrons. So when it absorbs an extra neutron, it's going to make that nucleus unbalanced. One product of fission uranium is Strontium-94. It's going to undergo beta decay, that's important, beta, with a half-life of 75 seconds into an isotope called Atrium. This also undergoes beta decay, and it takes 19 minutes, with a half-life of 90 minutes. Its product is stable, isotope of that. So write the balanced nuclear equation for the decay of Strontium-94 into Atrium. So we can see that we've got Strontium-94 there with a proton number of 38. So I'm going to start with that, 94, 38 strontium. It decays with beta decay. So that's a 0 and a -1 because it's a fast-moving electron, beta. So then when we put that Y then for Atrium, we've got to have 94 plus 0 is going to be 94. And then because it's beta decay, I need 39 here. So what's happening is we've got that fast-moving electron. So we've got 39 plus -1 is going to give us that 38 for 2 marks. Explain what is meant by this statement. It's got a half-life of 75 seconds. So for 2 marks, it's the half-life definition. It will take 75 seconds for the mass/activity for Strontium-94 to decay by half. Don't lose those 2 marks. Explain whether long-term safety precautions are required for the waste product of Strontium-94. Well, from the text, it says that it's got a half-life of 75 seconds. So the half-life is nowhere near long enough for any of them. So the decay, it's going to decay quickly into the stable, and that's what it said from the paragraph, that element quickly. So that's why we don't need any precautions. Last question then. This last question is momentum. Law of conservation of momentum for 2 marks. Momentum of a collision will equal the momentum after a collision, provided no external forces act. So it's almost like Newton's first law, in a sense that if no external forces act, something's going to remain constant. Well, it's the same for momentum. Momentum is going to equal before and after, so long as we're not putting forces on there. With this one, though, there is a force. Because it's swinging upwards, we've got to take gravity into account now. So gravity in this case is the external force. Discuss whether kinetic energy is conserved in both stages of the process. It's not going to be, because only in elastic collisions that happens. So some energy is going to get converted to heat and sound here with 2 blocks knocking during the collision. It's not an elastic collision, so the block will become deformed as well. So then that brings us on to possible 8 marks here for your calculations. So we need to look at this now in terms of an energy, because it wants to calculate velocity. And whenever we're dealing with potential energy, which was the gravity, so it's giving us lots of information here, and kinetic energy, you just need to realize that they equal each other. So the potential energy that's stored in an object, when it's converted to movement energy, is going to be exactly the same. So I've written a couple of things here. We've got the mass of the bee, which is the bullet, is 0.16. So we're going to need to convert that 16 grams into kilograms. The mass of the wooden block is 2.5. We've got the height, which is 0.119 meters. Again, converted from centimeters to meters. And then we've got the total mass is 2.516. So because I've got masses and because I've got heights and because I know gravity is equal to 10 meters per second, this is how I know it's going to be potential energy. And look at the formula sheet just to check the equation for that. So P equals mgh. I've got my mass, which is the total mass is 2.516, times my 10, which is gravity, times my height. That's going to give me 2.99 joules, or we can say 3 joules there. Now that I know my 3 joules, I can actually find out the speed by using this formula, because kinetic energy, like we said, is exactly the same as potential energy, which is kinetic energy equals half mv squared. Again, I'm getting this from the front formula sheet. I know my mass, and I'm going to come to, there's another way you could have done this for 4 marks, but I'm going to just do this a minute. So I got 2.99, which is my kinetic energy, which we just worked out, the same as potential energy, equals 0.5, which is my half, 2.516, which is my mass, times my v squared. When I rearrange for v, don't forget to square root it because it's v squared. It's going to be that over that, which gives me 1.54 meters per second. The other way you could have done it was, if you said potential energy, so you could have lined this up with mgh equals half mvk, mv squared, sorry. Because you have got masses on both sides, you could have actually cancelled these masses out, so the masses wouldn't have been required. Because sometimes, I guess you're unsure whether you use 16 grams or the 2.5 or whether they're both, but it's calculated velocity of the block after it's hit. I think the block swings through the height. So it's after they've combined. So the bullet's already into the block at this point. So we've got to take into account that that is the total mass. It's the mass of the bullet and the mass of the block. And you can see that clearly here. Look. So it's not swinging until the bullet hits it. And we want to know the speed that this is going. So we need to take the bullet and the block, the mass. But you could have done it without the mass if you're really good at maths anyway. So that was 4 marks, and then the last 4 marks is to calculate the velocity u, so the initial velocity of the bullet, the velocity at where before it hits the block. So we've got u there. So I've drawn myself a diagram now and we're going to use the momentum equation, which again is in the front of your book, page 2. So momentum equals mass times volume. So I've got my mass there. I've got my velocity, not volume. I just said volume. Mass times velocity, sorry. Okay, I got my velocities here. You can see that this is not moving, so this is going to be not effective anyway. I'm not going to worry about that. So I've got 0.016 u, which I don't know because I want to know my initial. That's going to equal, remember now the conservation of momentum, that's going to equal my total mass here, which is the mass of the bullet and the wooden block combined, and it's moving at 1.54 seconds. Now, you're going to get follow-on marks here. If you got the wrong answer here and you've put it there, they will give you the marks there. So you can see I'm just timesing that out. That comes 3.88, so and then it's just a case of rearranging. And we would have done that in class. So 242.2 meters per second. And that's the 2019 paper. I hope this has been of benefit to you. Thank you.